believe we are live. Are we live? I've got Ant from here telling me whether we're live. It says live. Excellent. I shall continue then. I've also closed the chat because Linux does not play well with Zoom, which is how we're doing the presentations. So, welcome to the madness that is present day. As you can see, I am dressed in my best cow onesie. This is sort of the level I am at. Past day 4, I think I've been stuck at home for 2 weeks now. And if you're following on Twitter, you might have seen earlier that I posted a tweet to try and understand y'all a little bit better. These were my 4 categories. And because I can't see you sitting in front of me, I've decided to reproduce you in the form of small objects I have lying around the house. So for the audience members who are nodding and smiling, we have the rabbit. There we go. Thank you to you. You are usually the ones I'm looking at in the first couple of rows to get energy. For the ones discussing with a friend, we have Gengar. It's going to go over there. Then we have, let's rather do this one for the people laughing at all my jokes. This is my little plant. And we've got this hand sanitizer, which is currently all the colleagues I forced to come watch. And lastly, the people who are about to leave is this small elephant, which I've made a small elephant to convince myself that you're not so scary when you walk out. I am currently sitting on, or trying to, on the Slack. So if you do want to drop a message or give a word of encouragement, I'm on stream 6. So yeah, but we're not going to continue talking about that right now. We're going to talk about Alice. Now, Alice is a software engineer. Can you tell? And Alice has a problem, a good type of problem to have, but a problem. She's working on a system, and the only way she can solve this particular problem is using machine learning. But it's great for Alice. You know why? It's 2015 when Alice worked on this project, and 2015 was a massive year in machine learning. For those of you who are kind of up to date, you definitely know of things like TensorFlow or Keras. And these were 2 examples of kind of the first libraries that were kind of used industrially that people were pushing. And they were released all in 2015. Additionally to that, you had things like Word2Vec or ResNet, which are kind of these primary neural network architectures. So things were great, right? So back in the day, I'd usually at this point ask the audience to figure out who had to build a neural network in C++. That was definitely me. I should post a poll. And in 2015, and now it's even easier, it takes about 3 to 4, 5 lines of code to code a neural network. There were loads of blogs, and we had this guy over here, Andrew Ng, and he kind of did this Coursera course, which went wild, and suddenly, you know, there was a hell of a lot of resources on this. So Alice was super excited, right? There was loads of tutorials, resources, kind of endless examples, fast-paced research. She was like, this is amazing. I am so excited to do this thing. So the first thing she came across was this term data science. Contextualize, we're in 2015 here. And Alice did her Googling and saw, oh, this is what a data scientist is. So data science is you're asking an interesting question, you get data, explore data, model the data, and then communicate and visualize the results. And she was like, great, that sounds like science. I'm a computer scientist, I can do this. Kind of understood this training, set of data, validation, tests. She remembered back to her days of building the neural network in C++. She was like, cool, I got this. She was ready. And then realized that this is all good and well, but how is she going to make this work in the real world? And that's what we're talking about today, is Alice's machine learning surprises, which we consolidated at the end to kind of a checklist for developers when building machine learning systems. Just so you know, I'm Jade. Thank you very much for joining me. I'm looking around as if you're in an audience I can't see, but thank you for joining. I work at Retro Rabbit, who are one of the DevConf sponsors today, as a machine learning engineer. I currently work on a product called Kaleido, which has a lot of natural language processing work, which is kind of dealing with text and machine learning. And then in my free time, I founded and run a project called masakana.io, which is kind of an open source collaborative research effort to do machine translation for African languages. So definitely go check it out if you're interested. But this is actually what I'm well known for, which is the dumbest tweet I have ever tweeted. And it somehow got 12,000 likes. I try to be a little bit more careful now. Unfortunately, I still post dumb things on Twitter. The other part of the story is I'm Alice in the original story. That was me. Still is me. Okay, so in terms of me being Alice, let's look at the different parts we're going to go through today. We're going to look at trying to deploy the model. We're going to look at what happens after you've deployed your model, and we're going to look at how you can try, improve, and maintain your model long term. Just a bit of context, I'm not going to be talking about machine learning models themselves. You can go do Andrew Ng's course, it's really nice. I'm not going to talk about which ones to choose. I personally work in deep learning and NLP. The requirements differ depending on what kind of realm and context you're working in. I've kind of been a one, up until this point, I've now got two people. I've been a one-person ML team working in kind of a startup context, and I work in a world of small to medium data, where data is sort of scarce and we need to collect more. I hear some people have big data. I'm sort of yet to see any of it, but great if you have it. I don't. I haven't had the privilege. So let's talk about the problem. Don't worry about the nitty-gritty bits in the middle there. What we want to focus on is what our problem was. We had this idea that you could specify a skill and someone would have a requirement for that skill. So I want to meet someone who can look after my cat, kind of as a free text field, you could put anything in there. And someone could say, I could provide pet sitting or cat breeding, software development of chef lessons. And the idea is that we're kind of building this matching system, which would say, someone to look after my cat and pet sitting should probably be a match, but someone who can provide software development and someone to look after my cat probably aren't a match. And some confusing things like someone to look after my cat and cat breeding, like sort of related, but not really a match. So should these people meet and shouldn't they meet? This is kind of what we wanted to predict. In practice, we're using a language model and downstream task. This is all technical jargon. In practice, we're using something called BERT, but don't worry about him. We're going to talk about the model. The model. So input anything in there, basically. So back to step one. So Alice had kind of smushed all this together. She got the results. She was like, yeah, okay, now what? And this is where we're going to dive into the story. Alice kind of surprises trying to deploy the model. So expectations, remember Alice, me, is a software engineer. And when we're building software, we kind of know this is what's going to happen, is we're going to, and then probably use some specification. In my mind, I was like, I'll just train this model. I'm going to shove a damn API on the front, and then I'm going to put it in front of some users to test, and then we're going to release it into the big wild world, right? And somewhere along the line, we'll also do unit tests. Always do unit tests. My first surprise was I came to my client with this thing, and he asked, "Is the model good enough?" And I said, "Well, we have a 75% accuracy." It's great, first try, 75%. And he's like, "Cool. Is that good?" I was like, yeah, I mean, it's a 75%. And he says, "Is it good enough for the product?" And I was like, I'm not sure, is it? And this is where I suddenly got into this realm of understanding what performance metric you choose. You know, a machine learning model outputs how well it's doing, which is this kind of accuracy or some sort of metric, but there were many options. And what became really important was that business needs to understand whatever metric you've chosen. You need to have an active discussion with them about kind of the pros and the cons, and you need to be able to get sign off. And you need to have this idea of a threshold selection strategy. That's a bit technical, but when you've got a machine learning model, it usually outputs like a probability of whether it thinks something is true or not. In practice, you actually have to put a fine line in that probability and say, well, if you're above 70% convinced that this is a match, then we'll pick it there. Or you can move that threshold a bit lower. So we went into this wild discussion for a bit and ended up choosing something called the area under the curve. which is very useful because the metric allows you to kind of engage with business, and they help you choose the thresholds, and it comes out based on their business requirements. So it allows you to kind of weigh up false positives, false negatives, and kind of get to a point. So that was cool. And the next question was, can we trust it? And I was like, what do you mean? It's giving this, we've agreed on the metric, you seem happy with it. He's like, yes, but how do I really know it's using the right information? And there have been thousands of examples of this kind of throughout machine learning history. So here we've got something that can detect cancer, skin cancer, and we've got one that classifies between a dog and a wolf. And what they realized is using some of these kind of explainability techniques, which I'll get into a little bit, that the skin cancer detection was actually learning rulers, because you always use a ruler when you're measuring a mole. So what it actually learned was a ruler detector. And what the husky dog detector had actually just built a snow detector and not learned anything about whether it was husky or dog. And the real example is that they went and took photos in a zoo, and suddenly their thing didn't work. I'm going to have a brief break to see what's happening on Slack. I feel very disconnected. Okay, nothing serious. Good to know. In terms of, so then we kind of use these explanatory tools. You can see the one here, the one that's kind of highlighted over here. It's highlighting snow was used. We use something called LIME. This tried to highlight what was important into making that decision. So in this case, probably should have made a better diagram. You can see this says, one is match, 0 is not match. So 1, this is definitely a match. And you can see what it used in that information was photographer and photography. This other one's really confusing. So here it's match snooker coaching with I want to meet an Excel teacher with expertise in financial modeling. And you can see that, that it's using financial and want in order to make this decision, which means it's learned some weird, spurious correlation. This is from a much older model. If you're doing kind of more modern NLP techniques, they tend to be a little bit more robust to this. But yeah, and it's arbitrarily picked snooker as something that it didn't want to match on, which is just generally a bizarre thing. But at least by building this, I could now go see, okay, something's very funny here. In practice, here are 2 tools you can look at. One of them is LIME. Another one is the What If tool. There's one by Google. And then there's, I think Microsoft has a kind of suite on explainability. These days, this is becoming more and more regular, and you should definitely be integrating these tools to figure out what's happening in the model. The next question was not actually asked at this stage. It was asked a year later, because in 2015, no one was asking this question properly, even though they should have been. And these days, we're trying to make people ask this earlier. You should be asking this question while you're designing the problem. Will the model harm users? And there's a new one of these every kind of week. So racial bias in a medical algorithm favors white patients over sicker Black patients. So this was a case from last year, September. They were triaging these cases in a hospital, and it favored white patients instead of sicker Black patients. So this is just one example of many. And I bring everyone to an amazing book by a wonderful author called Ruha Benjamin. And she says the following: racist robots, as I invoke them here, represent a much broader process. Social bias embedded in technical artifacts, the allure of objectivity without public accountability. And this is what happens, is people point to the box and say the box is objective. It's a machine, how can it possibly have bias? And we forget that it's being trained on real world data, which actually does have internal biases in it. Another really good article, Don't Believe Every AI You See, what are the unintended consequences of designing a system at scale on the basis of existing patterns of society? And that's sort of the question you really need to be answering. That particular article gives quite a good guide on how you should think about harm and machine learning models. In our case, we looked at some of the tools we were using. We were using Word2Vec somewhere, which has known gender and race biases built in. It's in English, which means we're only accessing or only allowing a certain group of people to work on our platform. Is it robust to spelling errors? So are we making kind of biases unintentionally towards people with lower education? And how does it actually perform when given malicious data? Can it hurt? And it's really hard to mitigate these bias. And there's constant research in this realm around this. So instead of at this point saying, can we get rid of it completely? There are some ways to mitigate it. Let's at least measure it. So at least we know, and we know when it's getting better or worse, and what we're doing is making a difference. So first step is try to see if you can measure this. There are loads of tools now coming out. Google's got one playing with AI fairness, Code. IBM's got another one, so one in the middle, which is AI Fairness 360, and Fair Learn, which I believe is Microsoft's. And there's a nice list, thank you to Pelanomi, who gave me this list of awesome machine learning interpretivity tools, which is just loads and loads of them. You should definitely start using them. So yeah, so revisiting the expectations. Time, all right. This is what I expected, and this is actually sort of what happened, is we had to first choose our useful metric, evaluate the model, we'll build the model, evaluate the model, choose the threshold, explain our predictions using an explanation framework like I've shown you, and kind of put in a fairness framework so at least we knew what we were doing. And like I said, this actually didn't happen then, it's happening now, but you should do it then. You know, put the model, did some tests, put it in front of users, and then we got it deployed. So at this point, we have model deployed. Great, hurrah, success, very excited. Let me have a water. And a quick chat to see how discussion is going. We are silent, which to me tells me that's a good thing and we're not having too many technical issues. Okay, surprises after deploying the model. We've deployed it, now what? Once again, expectations as a software dev. There'd probably be some bugs submitted or complaints from users that would go into some tool. We triage those bugs. Those bugs will be picked up in kind of a agile cycle of reproduce, debug, fix, release, etc. Maybe we'll observe some user drop off and we can use that to figure out what is happening. And that was sort of the expectation. First surprise. I want to meet a doctor and I can provide marijuana and other drugs which improve health. These people matched on our system. And the client comes back and says, well, the model's got a bug because it's matching these people. And, you know, clients are used to talking in bugs because it's software. And this brought on a whole philosophical phenomenon. What is a model bug? How do we fix said bug? When is the bug even fixed? We're not working with yes and no in machine learning. We're working with kind of a broad continuous space of options that could happen. How do I ensure a test regression to make sure that like this thing is actually fixed? And how do I even determine bug priority? What does that look like in machine learning? So we go back to this, I want to meet a doctor and I can provide marijuana, other drugs which improve health. And the first thing we want to do is describe it. So usually you describe that in kind of a use casey bug description log sort of thing. What did the user do? When we're describing machine learning problems, to me, it's capturing multiple cases that kind of show you the extent of the bug. So what we did is we took the original case and said, okay, well, the prediction was yes and it should have been no. And we kind of adjusted them, we tweaked them a little bit and said, okay, what happens if I do this? What happens if I do this? And then in doing this, I'm building up a little set, a little data set, which describes my problem. And each of these can come together, kind of form a test case. And you can see on the side here, I've labeled with false positive, false true negative. These are kind of giving a feel for where it's going wrong. And traditionally what you do is you'd write in code, you'd write your 10 tests and add them to your test set. Here what we do is we add them to our test data set. So now our test data set is growing as we're learning about the way our users are using the platform. I always say your test set, and this is something I also learned from Andrew Ng in a really good book called something which I'll post later. And he goes on about your test set is your problem description. Usually, often we say our unit tests are our problem description, or our business documents, whatever our problem description, our stories. In this world, your test set describes your problem that you're actually trying to solve. So this is what the first step we do. So we actually built a little interface that would allow our product owner to come and kind of log these bugs and kind of describe them himself. So we've got a name, kind of when it was created, you can see how old this is, and we've got a whole variety of test patterns that they can add and say what the expected behavior is. And this was really cool because it allowed me to figure out, is the bug fixed? Because fixed, like I said, is tenuous. We've got, sure, it might handle that one case. We could add an if statement to handle the one case, but that's not really the issue we're talking about. So what we did here is, if we've got, these are kind of our models that we're retraining, because you build a model, it's probably not perfect. You need to build another one, probably with better data or a different type. And so these are the candidate models over time. To me, a candidate is someone where it's a model we're expecting to release. And this is some sort of error on the side. So this should be as small as possible. And we can see what's happening. And people don't tend to think of this, because the question my client came to me and said, cool, you've added all this data and you've gone and you say that you might have fixed the problem. Is it fixed? To what extent? And then later on, I'd train a model further on fixing a different problem. You'd be like, cool, so that other problem has come back, or it's gotten worse, or it's changed behavior. So what we did is we plotted this, and here you can see this enabled the client to go, I see you've improved on our drugs doctors false positive issue, and it's gotten worse on politicians, but he would say, frankly, I don't care about the experience of politicians on the app, and I'd much rather that people had a safer experience. So let's choose your latest model to use. So that was quite useful. So now we've got a whole bunch of these bugs, right? As a user, it's cool to know this information. As a client, it's good to know how it's performing. But now I've got to pick one to work on, and this is the view I have. And this is only maybe, I don't know, a third of the ones that we had when you reach this problem. Which is the one you need to pick? So you could pick, well, the one that's got the worst error is the one that you should work on first. But it doesn't really matter if only 2 people are affected in comparison to maybe one that's only mildly affecting other users. And maybe you want to work on that one instead. So the way we triage, or we chose to triage the bugs in this case, was the percentage of affected users multiplied by the normalized error, multiplied by some sort of harm factor if it was actually going to cause harm, just to make sure that we're dealing with those really early on. And this could give you a nice little graph. So let's say each of these are our issues that we're dealing with, and we've got a number of impact errors. We can sort by that and just pick the problem to work on first. So in our case, arts being too general was a thing. We'd match people who are painters to musicians. That was useful. So looking at this, we say, okay, good, take this, go look what the problem is, go get more data, go create new features, etc., the kind of standard data science process from there onwards. Once again, how we're doing for time. Give everyone a breather. Later on, you can play this talk at half speed so you can hear what I'm saying. Is this model better than my old model? That seems easy, should be. I've got performance metrics. I've got this number that I can just compare. But it can get hard in our sort of process. And I bring this up because I've seen this mistake been done loads of times in organizations, and they're doing it and not realizing they're not comparing apples to apples. So in our world, we have this changing test set, which has to change because it has to keep up to date with what users are adding and their behavior. Data drift, they call it. And let's say we get these 2 performance numbers. Let's say bigger is better. So 0.8 and 0.75. So Tweedledee is 0.8, Tweedledum, the newer one, is 0.75. In my mind, I can go, oh, okay, Tweedle, the older model is better. But we need to be cognizant that we can't use old test set data. We cannot use the old values if our test set has retrained, if our test set has updated. So what we really need to do is reevaluate all our candidate models to really do a comparison, a fair comparison. So now Tweedledum's metric is actually a little bit lower, and it's clear that Tweedledee's metric on the right there is higher. So now we actually have a fair comparison of apples to apples. Next issue. Client, I demoed the model yesterday and it went off script. What do you mean it went off script? He said, oh, he has a demo script which he knows he'll get certain certain results, and that helps him, you know, kind of talk through the different parts of the system. He goes, what changed? And I was like, well, we did a whole bunch of work. We added some data, we added some features, we deployed new code, we ensembled some things. And he's like, yes, but I need you to go back because this is clearly not behavior that is good. This is one of the main sales points we're doing. So can you figure out what happened? And I'm like, well, I've done 20 things since yesterday, since I deployed this model. Why is it doing something differently? Which one? Was it the data that updated that I used to train the model? Was it my model that got trained? Did I use a different one? Was it the pre-processing that got changed? So how to figure this out is the trick is you've got to have some sort of experiment management. And if you were in Nat's talk this morning, he went through in detail many of the tools. At the time, this was 2015, as you might remember. And in 2015, then none of these tools existed. So we built our own. And kind of what I want to highlight here is that kind of the core concepts, which they kind of bring into a lot of these other tools. So some of the core concepts are you've got a data repository. This tracks versioning of your data to some extent. You've got a code repository, it tracks versioning of your code. You've got a model repository, it tracks all the models, and you've got some sort of results repository. And you've got a metadata store, which allows you to kind of tie all these things together. So at this point, I know I can go look back and say, okay, so the model you were working on was model 3. Model 3 was related to this data. The model that you had when you were originally happy with was model 2. What changed? And I can now go interrogate what changed in my data, what changed in my code. I can compare the results. And this was super key. So ML Flow is one of the tools that does this really well. There are a couple of others, like everyone's catching on that this is a nightmare that needs to be managed. So once again, step back to our expectations of the world, and this is where we actually are. That's big. Yep. So here, this kind of summarizes what I went through. Identifying what your issues are, which is logging your bugs, describing them with test patterns, adding them to some sort of model bug tracking tool, whatever you want to call it, calculating some sort of priority and triaging them. Then as a kind of in your agile sprint, as a developer or data scientist, you pick which problem you're going to work on. Do one of the things that make the model better, which is either gathering more data, changing the model, creating features, retrain, evaluate against every other model, look at the individual problems, whether it's improved on your bug, and then select the model from there and deploy. So that's kind of actually what happened. How much time? I'll answer that question later. Cool. Surprises, maintaining and improving the model over time. So this is kind of the long-term view. You hit this much later. Expectation is, like I said, we found this a way of you pick an issue. And once kind of answer Reynard's question on Slack is when you've picked a problem, there are multiple ways to try to solve it. So one of them is figure out what realm this area is in and go generate more data. The next option is adapt the model. So this could be adding if statements. I'm not joking. I had a conversation with a bunch of people at Google, and they were saying, I was like, what happens if your model really behaves outlandishly on something weird? And they were like, yeah, we add an if statement. So even Google does that occasionally. So sometimes you have to add an if statement. Sometimes you can put a more robust model, or you can do some better hypertuning, or you can add more features. So those are typically the ways. In our case, we needed more data. Generally, a reason the model wasn't performing well is because you didn't have enough data on that particular area. So what you do is you go generate or select unlabeled patterns, and then you get them labeled. And there are a whole bunch of tools which go and do this. So Mechanical Turk does this. There's about 10 other ones that will, crowdsourcing tools that label your data. So once you're labeled, you take your labeled data and you add that to your training data set, and you can train the model. And my expectation was everything would just get better and better, and it would be lovely and magical. I was so excited. My first problem was realizing that our user behavior sort of drifts. So things that they keep coming up with unexpected things that we hadn't planned. So we'd be targeting one type of client, one type of enterprise, and selling it to them, and they'd all be software engineers, and we'd specialize in that. And
designers and everything's geared towards that. And then we'd onboard a NGO and they'll have a completely different set. So our space of users and customers and domains completely changed. So the only way we could get around that was making sure we're regularly sampling data from production for training. And we're regularly refreshing our labeled test set from production and continuously sampling from it, which is kind of a policy you have to put in place. Like, how often are you going to do it? Can you track this live? The next surprise was these data labelers, who are just very, really experts. It's one of my gripes with Amazon Mechanical Turk, because I cannot get kind of shortlist people I'd really like to work on the problem. I can only blacklist people. Say I don't want them to work on it. So I want to say, okay, these have done really well. Let me ask them again. We'll pay them a higher fee. So data labelers are kind of really experts. So what in practice would happen is we generate data, we try to get it labeled, and they label terribly, and you'd add that to the data set, not realizing, and all your metrics would get worse. And then thankfully we have version control in place, so we can go back to an older version of the data and say, okay, yes, ignore everything that was done in the past 24 hours. But yes, so that was fun. And the last prize was that the model was sort of not robust. Let me talk about how we solved this a little bit. Sorry, ahead of myself. So what we did here is we just kind of put an interface, a step in between. So every time we got results in, we had to have a data scientist go sample each labeler's data and kind of reject or approve them based on the quality. So we'd have to have a kind of filter step to just relabel them. I've seen other places where they say, oh, well, let's get 3 answers and just kind of aggregate them. That works sometimes, but also it creeps in, particularly if you're looking at really high quality data and it's not generalizing very well. The last one is that the model is not robust. These days, as ML gets better and better, it's getting more and more robust. But often you end up with a model that isn't robust. And by robust, I mean, it's sensitive to changes in case in NLP. So capital letters or small letters. Or it's sensitive to unknown words it's never seen, or unknown characters, for example. And by sensitive, it means that adding those in make the model go completely haywire, even if it's a single word change. And what we learned is that sometimes your model does know when it doesn't know. It doesn't always, which most of the time it doesn't. But sometimes it'll tell you, it'll give you a very mixed outcome, saying, oh, I'm 50% convinced this is something. And that tells you that it's uncertain about something. I mean, there are a variety of ways for kind of detecting and measuring robustness and uncertainty. These are all really technical kind of things. So if you're interested in the screenshot and go read up, I'm not going to spend too much on them in detail. I'll spend time on the last one because this is one of the easier ones to do, is kind of add some noise to your data. So a little bit of noise, and see if that greatly affects your output. If that greatly affects the predictions that your model is making, you probably don't have a very robust model. And to actually deal with this lack of robustness, sometimes adding noise to the data is actually a way to train it up. I really like this PhD thesis by Yaron Bell. Not everyone has time to go read a PhD thesis, but it's really great. The blog post is excellent, so I do recommend it. So surprise 11, getting towards the end here, it just gets worse and worse. Kind of changing and updating this data so often gets really, really, really messy. So if you're bringing in users and now you're maybe adding features and you're labeling different types of problems, and it gets pretty chaotic. You put different formats. Often when you're storing machine learning data, because it's quite big and often unstructured, it's not stored in a nice, tidy little SQL database. I would love everything to be stored in a nice, tidy SQL database. I feel a lot better if it is. So kind of changing and updating your data gets really messy. So we realized that we kept having things. So we'd end up with bad values in the data. We'd end up with weird distribution shifts of what we expected. We'd end up with kind of data leakage. Data leakage is a machine learning term for kind of cheating. If your model has a pattern in their test set that also occurs in the training set, then technically it's trained on something it already knows. So it's cheating. It didn't actually generalize well. It knows what you told it. So kind of we needed this sort of stuff kept happening. So what we did is we put it on GitHub. So it was on GitHub large file storage, which was our data version control tool of choice. And we'd run CI on it. So we had unit tests. We were unit testing our data. So this was plausible. Once again, small, medium-sized data. I don't have giant streams running everywhere. I've got kind of stuff that's very manually updated. And here we would run like audit checks to make sure that we had our data was happy. And this was really helpful. It seems so silly, but it was super helpful. Yeah, so my expectation of this is how we're going to make the model better actually turned into this saga of picking a problem, generating, selecting unlabeled data, go get the data labeled, and you can just get the model, go label the patterns that the model was told you it was uncertain about. So that's what we did. We said, okay, when it said it wasn't convinced about this, we kind of said, okay, make sure we get that data labeled too. Review and sample each data labeler to make sure that they're of good quality, kind of escalate conflicting labels to an expert. Our expert was our product owner, who we created a little interface for. We photoshopped his face onto Mechanical Turk, Mechanical Turk that photoshopped his face, and he would go label the data, so would I. And then we get some new data. We put that in some sort of branch, because I have a branching mechanism, because Git, and we run tests on the data, and once they've passed, we've merged into the main data set. So that's actually what it turned out to be. So that was fun. So on to the summary. You can all step back when you've got some time. I don't have the chat open. Step 1, careful metric selection with your client involvement. Next one, a threshold selection strategy. Once again, best with your client involvement. They've got business expectations. Explain your predictions, so explain what the model is doing as best as you can using a explainability tool, put in a fairness framework, have a ML problem tracker, so you can track any bugs that are appearing, kind of a bug triage strategy, whatever that might be. Make sure your training is reproducible and you can compare the results. Make sure you've got result management, and the key one is answer why. Machine learning doesn't tell you why anything happens. Be able to answer at least why something changed to your client. So why did this get better or worse? And I could go, we updated the model, or we updated the model and added this data, whatever it might be. So being able to answer why and having the kind of good ML pipeline with all our experiment management is really helpful. I have a strategy on refreshing your data from production. If you're not automatically doing that, I know some systems automatically do a time series, particularly susceptible to it. So I have data version control, have CI and CD, or some sort of metrics to track for your actual data. Data quality, distributions, a data labeler platform and a strategy to deal with your data labelers, and then kind of a mechanism for understanding how robust your model is or how uncertain it is. Things I didn't cover in detail, but these are all nicely Googleable. Some of them have even put direct links in. So kind of these pipeline and orchestration tools, which I've mentioned. Kubeflow and MLflow are two really good examples of this. Kubeflow is probably more complete, but you have to use Kubernetes, so it's a bit of a learning curve if you haven't before. MLflow is very modular and small and customizable, so I tend to use MLflow. And then end-to-end products, so TFX is Google's, SageMaker is Amazon's, JRML is Azure's. I'm not going to express a preference because that's literally the talk I did last year on clouds and I upset people, so I won't express a preference. Unit testing your machine learning systems, I didn't do in detail. It's really important and really hard to do. I do recommend testing your ML pipelines by Christina Gorgieva. She's South African, but she's actually working in Berlin or London now, who knows. But great post. Debugging your ML model, so when it's gone wrong, what do you do? That is the guide. So a field guide to fixing your neural network model by Josh Tobin. Privacy, didn't talk about that. It's also really important, more and more important these days. Google has come up with a strategy which is very cool, very robust. So check out Google's federated learning. In terms of hyperparameter optimization, which is a way you tweak your model to make it better, there are so many tools and I can go through those. So that's the end. Thank you very much. I will take questions now. I don't know how much time I have. And I need to bring up the chat. So I'm going to stop sharing my screen. So take a screenshot of any information that you might find useful here. And then I will move over to chat. Ooh. Okay. And you can probably see this now. That's probably fine. Okay. So Cool. Question 1. When discussing performance metrics, target thresholds, did you translate that to or from simple natural language implications? 9 out of 10 matches will make sense. Not at kind of a performance metric level. So what we did do, so we didn't go quite low to that level. So what we did do is look at the number of false positives. So false positive is something it shouldn't have matched on that it raised. And if you think about things like health, you don't really want to be giving people false positives that they have a disease and then they don't. So you need to make sure you'll have very few false positives. Whereas if you're building kind of recommender system, then you can actually build it the other way. In terms of question 2, malicious data. So malicious data, I mean, so there's 2 ways to think about it. In our case, it was a malicious, not malicious, but an illegal user trying to solicit drugs on the internet, versus malicious data, which is actually trying to attack your model. So you can give machine learning models certain data that actually is an attack. I'll post some links on the chat around it. It's very fascinating. It's called adversarial attacks on machine learning models. Very important to do, particularly if you're working in like a self-driving car realm. How do you identify outliers in your model? And when do you say those data outliers are useful for training your neural network or remove them? So I thankfully work in deep learning, so your outliers very rarely throw it off completely. In fact, deep learning tends to ignore outliers. In terms of how would you identify them? So usually people do this through a number of unsupervised techniques. You can determine if someone's at the end of a distribution. In terms of data sets that apply social biases, how do you identify those biases? I would suggest going and looking at the tools. They allow you to kind of check what the output of the model is doing on specific demographics that you may care about. Have you had to do data labeling for personally identifiable information? No, I've never had to do that. If you were there any platforms that work for you, or did you go in-house? No, I haven't had to do any. In fact, we explicitly try not to use personally identifiable information in most of the models. The ones that, I think we would probably go in-house, depending on how sensitive it is. I do know there's work being done by a company called Sabens.ai. And they're really great. So definitely go have a look at them. And you can also talk to the guy who runs it, and he's very concerned about privacy. So he can probably give you something interesting. And have you ever had end users try to exploit your models to appease the algorithm? Yes. We don't know if they were doing this on purpose, but what they do is we'd get those those posts you get on the side of the road about, which doctor, bring back Loft's lover. We got these massive long descriptions like that. And sometimes, depending on what it was, the model would completely swing to the other side and actually start matching them furiously and giving them loads and loads of matches. So that was fun. That was easy to fix because we just, first of all, just posed a limit on it. Good versus bad labeling. Yes, so it is subjective, but in this case, it was pretty much defined by our product owner. So in our terms, we knew what a good match was. We had definitions for it. And a bad labeler was someone who would not really pay attention to actually what the labeler was doing, like what the content was. So you could see there was, like, I wouldn't, for instance, get annoyed if someone said there was a match between a software engineer and a data scientist. What I would get annoyed if someone said there was a match between this plant and this hand sanitizer, which is the sort of things that we were getting. So that is kind of my examples, is people who are not following the problem statement and are just kind of almost behaving randomly, which you see sometimes. Cool. So yeah, I think that's the end of me. Thank you very much. I will be hanging around in stream 6. I will see if I can organize, if you can't get hold of me on there, you can get hold of me on Twitter. We'll also post it on the chat if you didn't see it. Yeah, and this is fun. Have a great day. I'm having a great day myself. I hope you guys are too. Speak to you later.